All right. So like I said, we're gonna learn how to describe complex numbers a different way. Okay, it gives you the same location, it's just gonna look different. All right, so what we know so far is if I gave you the point 3, and I said, hey, plot the complex number 3. So everyone would go 3 on the real number, and they go up 3 on the imaginary, and that's where that point is. Okay, so what we did was we used rectangular coordinates to get that location. All right, so let's see. When I say rectangular coordinates, what I mean is we're using an X and a Y. Okay, so to get the location of this, we went 3 on the real number axis, and then we went 3 on the imaginary axis, and that locates this point. Okay? All right, so that's how we could locate a complex number. So what we just did is what is called a using rectangular coordinates. So if I said, hey, plot 3 plus 3i, everyone would plot the point 3, 3. That's using rectangular coordinates to describe a complex number. All right? Okay, now here's the other way of doing it. So eyes up front. Watch. So instead of using numbers like 3, 3 to describe that location, we can describe it another way. Okay, and that other way involves trigonometry and is called polar coordinates instead of rectangular coordinates. Right now, these are rectangular coordinates. Okay, well, the way you do that is you change the shape of this grid. So I'm going to click on the little, whoops, the little gear up here. And now my grid, you see how you got 2 choices on the grid? The grid I just used and this grid. Okay, now the way that I could describe the location of this point, I could say this point is a certain number of degrees from the positive real number axis. So what I mean by that is this. Let me take a snip. Okay, I can describe that same location. I just did it using 3, 3, but I can say, you know what? Instead of using coordinates, I'm going to describe that point by rotating that ray. Okay, that's a ray. So how many degrees would I have to rotate it so it goes through that point? Yep, I'd have to rotate this 45 degrees. And when I do that, it's going to look like this. Okay, now what I have to do is I want to locate this point right here. Well, I said, you know what? To get to that point, rotate 45 degrees and then mark off whatever this distance is. Well, that distance would be the hypotenuse of this triangle right here. And if that's 3 and that's 3, then that hypotenuse is going to be the square root of 3 squared plus 3 squared, 9, 9, 18, and that would be 3 root 2. So then I'd say, okay, go out 3 root 2, and that's your dot. Okay. So what this is doing, this is describing this point using an angle and a radius. Okay, the other way that we did it up to this point was using a x-coordinate and a y-coordinate. So this uses an angle and a point, and the previous one uses an x and a y coordinate. So, come on, catch up. This is called rectangular form, and this is called polar form. So what we're going to learn today is I can take something that's rectangular, like this, yikes. Okay. And I can say this is the complex number in rectangular form, and what you're going to learn today is it's the exact same thing as 3 root 2 cosine 45 degrees, comma, cosine sine 45 degrees. That's the exact same point. So this is describing the point using a radius and an angle. And it's the same place. This is describing the point using an x and a y coordinate. So you can describe the same location using an angle and a radius, or an x and a y coordinate. So the x and the y, the angle and the radius is known as polar coordinates. Okay, that's what this is right here, a rotation and a radius. Okay. Alrighty, so I can describe anywhere on this chart the exact, just like I did when it was rectangular coordinates. All right, so that's the purpose of what we're doing today. All right, so to accomplish this, we're going to use, instead of xy coordinates, to describe a complex number, so instead of using x and y to locate a complex number, we're going to use an angle and a radius. To do the same thing. Okay, this is called polar form of a complex number. Okay, which is probably something you haven't done before. So if someone said, well, what's polar form mean? you're just describing the location of something using an angle and a radius. So you know how on a map we use X and Y coordinates? Well, you could also describe locations on a map using an angle and a distance. Okay, so for example, you ever heard, like, if you're watching a movie and they'll say, hey, we have an unidentified aircraft bearing I don't know, 140 degrees at, I don't know, 30 miles. That's polar coordinates. Okay, a bearing of 400 degrees or 140, you start up here and you go this way 140 degrees. Then you would draw a line 30 miles that represents 30 miles, and that's the object. So that's what this means here. That's polar coordinates. You're using an angle and a distance to describe the location of something. Okay, if I was trying to describe where Tucson is in relation to Phoenix. Phoenix, Tucson. I'm just guessing right now on if I drew it right, but if I connected these, this would be the bearing to Tucson. I'm guessing maybe that's like 150 degrees. And then, I don't know, it's like 100 miles. So get on a bearing of 150 and drive 100 miles and you're going to end up in Tucson. You're describing it using an angle and a radius, a distance. Okay, so we've got this drawing up here. These are all, this right here is rectangular form. And what you're going to learn that right there is identical to this. This is called polar form. So two different ways of describing the same thing. It's like saying hello and hola. Mean the same thing, look different, sound different, but are the same thing. All right. So you're going to learn today how to take something from this and make it look like this. All right, so let's lay the groundwork on how you do that. Pardon me? Are you even listening? You're talking. Okay. So now, if I take this complex number, its rectangular form would be -3, 0. Okay, so that's this point right here. This is its modulus. So its modulus is 3. That's easy. And its angle of rotation, remember, we always start at the positive real number axis, that's right here in yellow, and we always rotate counterclockwise. So the angle of rotation for Z1 would be 180 degrees counterclockwise. All right. right? Okay, now the next point is 0, 2. So it would be the rectangular coordinates 0, 2. Okay, and its modulus, well, its distance is just 2, so that's easy. Okay, and its rotation is 90 degrees counterclockwise. Okay. All right. Then we got Z3. So that's 3, 3. Okay, so we'd represent this using a 3 and a 3. Okay, its modulus we already did. This distance was 3 root 2. So we already knew that. And this rotation had to be 45 degrees. Any question on how I'm getting 45? How did I know that was 45? It looks like it's half, okay, but my drawing could be off. What is it about this triangle that tells me it's 45? Cameron? That's 90, yeah, but what makes these 45 and 45? How do you know? Yeah.
All the sides are the equal length.
Right, this length right here is 3, and this other length is 3. So if those two sides are equal, then these two angles are equal. So those have to be 45. Doesn't have a choice. Okay, so this is a 45-degree rotation counterclockwise. All right, now let's do this one that's here at 4, Z4. All right, so Z4 is the point, the rectangular coordinates 2, negative 2 root 3. So on your paper here, sketch a right triangle. This is 2. And this is negative 2 root 3, which is just a little bit longer than 3. Okay, so now what's the modulus? That's this dotted line. What's that length going to be? Anybody know, like, lickety split without doing any math?
30.
How long is it? Its length. So it's not you're not going to give me a degree, you're going to give me a length. Like, is it 3? Is it 5? Is it 4? Well, if we don't see it right from the get-go, then we can do the modulus, right? The modulus is just a squared plus b squared. All right, so let's do that. So I'm going to do the square root. A is 2. B is negative 2 root 3 squared. Okay. So that's 4. Okay, now what's 2 root 3 times 2 root 3? Anybody? 2 root 3 squared. 6. Okay, 2 times 2, 4. Root 3 times root 3. 3. Because it's really root 9, and the square root of 9 is 3. So this is really 12. Root 2 root 3 times 2 root 3 is equal to 12. Okay, and then you add those up. Yes?
Where'd the negative 2 on the 2 go?
Because why is it 2 root 3 down?
No, where'd the 2 go in getting 12?
Oh, because I did this. I did negative 2.
Oh, hold on, I get it now. I thought that was the whole.
Okay. You're okay now?
Yeah.
So square root of 16 is 4. So this length up here, guys, is 4. All right. Now, what's the rotation? So the rotation is going to be this. 270. Well, 270 would be to here. So it's more than 270. It's more than 270. 200's less than 270. So 90, 180, 270. So it's going to be a little bit more. How did you get 300? It's a pretty good guess, because that's what it is. Did somebody have it over there? You are. Okay, say it again. Oh, that's all right. Okay, so how do you know? Was it just a good guess, or did you figure out that it was 300 another way? Just guessed. Okay, good eye. Good eye. Okay. So Norvin, how did you come up with? Did you just kind of eyeball it? You looked at what chart?
On the floor right there. I got a chart.
Yeah, exactly right. He looked at the unit circle. Okay, and how did that tell you that it was 300 degrees? So I'm going to look at my unit circle here. Let's see. So you looked at the unit circle. Okay. And what? You just kind of, it kind of looked like that? Yeah, that kind of works. The thing, though, is that instead of these numbers being 1/2 and this is 2, and this is negative 2 root 3 instead of that. Okay? All right, so you could do this one 2 ways. Okay? The other day in class, we figured out what the angle was by doing the tangent. So if I took my calculator and I did the tangent, let's see, back here. Let's see, we can just do it on Desmos real quick. Okay. I'm going to go inverse tangent. So you see, I go to function, and I pick tan -1, and the tangent is equal to the opposite side divided by the adjacent side. So this angle right here this would be the opposite side, and this would be the adjacent side. So I'm typing this in. Opposite divided by adjacent. That simplifies, and it becomes this. You with me? Okay, now when I type that in, watch what I get. What did we say? This was -2 square root 3. And then I'm going to divide that by 2. And you see what you get? -60. Or if we use Norvin's method, check this out. You see the tangent right there? Oh, you can't see it. Hold on. I just circled it. The tangent is -√3 right here. And that point is -60 degrees. So you could have just looked up, where's the tangent, -√3, and that's my angle. Okay, so lots of ways you could come up with that. Whoops. Alrighty, so back to this. This angle is -60, but that's -60 clockwise, and we want it counterclockwise. That's clockwise, which is the same as 300 counterclockwise. So now you got the information you need to write it in polar form. Okay, this is the modulus. Okay, this is going to be the same thing as the radius. And that's how far to rotate. So rotate 180 degrees and mark on it a length of 3. Rotate 90 degrees and mark it at a point 2 units from the origin. Rotate 45 degrees, mark it at a point 3√2. Rotate it 300 degrees, mark it at a point 4 radius, 4 out from the origin. Go to 300 and then measure 4 out. That's the location of that point. Okay. That's what that's doing right there. Okay, all right. So we got this by we did it using the tangent. We did the inverse tangent, which is opposite over adjacent. That's how we got the -60. Alrighty. Okay, can I move this? You guys got a copy? Alrighty. Now, it says, can you find 2 more rotations that would map a ray to 3,3? Alright, now, from the front, we know that if we took 3,3, it was the same as the complex number 3 plus 3i. Okay, and we called this the point, I think it was called Z, what was it? Z3. Okay, so we described Z3 as having an angle of 45 degrees. So what this is asking, could you take this and use a different angle that lands at the same place? So instead of going 45 degrees, what's another rotation that you could have done and be at the exact same place? So the first one was this, go 45 degrees.
Go 405 degrees.
How did you get that?
360 is a full rotation.
Yep, exactly. So you could have gone 45 plus 360. So that would have looked like that. That works. That's 405 degrees. Okay, what's another way?
360 plus 45.
Yeah, that would have been counterclockwise. Let's stay or that would have been clockwise. How about another one that's going counterclockwise? Yeah.
315 counterclockwise.
Well, no, let's stay counterclockwise. 765.
Wait, I got it.
Man, you are on fire today. Okay, 765. So there's an infinite number. You could keep going. Just keep adding multiples of 360. So if I took my original angle and I just added multiples of 360, I'm going to get another angle. Yeah. So it says find at least two. Well, there's actually infinite rotations. Because you could just keep adding 360. So there has to be some sort of agreement, well, which one of those do you use? So what we say is the angle that you're going to give is always going to be the one that's between 0 and 360. Okay? So to eliminate all these possibilities, you use the one that's between 0 and 360. Okay, all of these rotations are just 45. It says how are they related? Well, they're all 45 degrees plus some multiple of 360. So always pick the one that's between positive 0 and 360. That's why we didn't use negative 60. Okay, all right, almost done for today, guys. Okay, can I move it? Okay, so now what we're going to do is do a little quick review of right triangle trig. All right. If we were going to describe, this is using, these are rectangular coordinates. That's a rectangular coordinate, that's a rectangular coordinate. Now what we're going to do is instead of describing those using x and y, we're going to describe these using this angle. Okay? All right, so if z is located at, so z is located at some number x and some number y. Okay? Now, another way of describing where z is using the angle. Mm-hmm. All right. So, do you guys follow that this x coordinate right here is the same length as this side? That's equal to the length of the adjacent side. Okay, and the y coordinate, that's equal to the length of the opposite leg. Okay, that's this side, let's say in purple. Okay, this is the opposite leg of that right triangle, and this is the adjacent leg of that right triangle. So you can get those numbers if you know the angle and using sine and cosine. Okay, so this right here is the length of the adjacent leg. And this is the length of the opposite leg. Okay, so let's figure out what those lengths are. Okay. All right, so if you remember your trigonometry here, the sine of an angle is equal to the length of the opposite leg divided by the length of the hypotenuse. The cosine of an angle is equal to the length of the adjacent leg divided by the length of the hypotenuse. And then the tangent of an angle is equal to the length of the opposite leg divided by the length of the adjacent leg. All right, so this right here is the same as the y coordinate. That's the exact same thing as the y or the opposite leg. Okay, so take that equation and solve it for the opposite leg. Well, let's do this first. Hold on. Sine. This is the opposite leg, which is what coordinate? What letter? X or Y? Okay, so I'm going to take out the word opposite and I'm going to put in the letter Y. I'm going to take out the letter or the word hypotenuse and I'm going to put in the letter R. Now I'm going to do the same thing here. Cosine. I'm going to take out the word adjacent and put in X. I'm going to take out the word hypotenuse and put in R. Okay, now solve this equation for the letter Y. What would you do to both sides? How would I get Y by itself right here? By R. So if I did that, I get Y is R sine theta. So this becomes r sine theta. And do the exact same thing to this. Multiply both sides by r, and I get r cosine theta is x. R cosine theta. So what you just did, you took x and you turned it into an angle times a radius. You took the length of y and you turned it into an angle times a radius. So we can, z is located at the radius times the cosine of the angle, and your other coordinate is the radius times the sine of the angle. That's the exact same thing. This is your x coordinate, and the second one's your y coordinate. But now it's using a radius. This uses a radius, or this uses an angle and a radius is what we were trying to do. Uses an angle theta and a radius r to locate a point. So that's how you get the polar form of a complex number. R cosine theta, r sine theta. All right, you guys have been pretty good. You've stayed most conscious. That's pretty amazing. All right, appreciate it. So we'll pick up with this tomorrow. Okay, so remember you've got